Good afternoon. My name is Hamzah Abdullahi. I am part of a project team consisting of myself, Josh Hoffmann, Raamish Naveed, and Harpreet Saini. We have spent this last semester working on a device called the Spinal Stiffness Indenter, or SSI for short, under our client Dr. Kawchuk, and we'll give you a brief intro on the project as a whole before jumping into a demo of it in operation. Let's begin with some context on why this device is necessary in today's world. People with back pain often have spinal stiffness. Spinal stiffness can be measured and be used as an indicator for spinal health. Traditionally, it can be measured using a device called an indenter. This device gently presses into someone's back and measures both the applied load and how far the back has been displaced. The data measured in a given session includes both the applied load and how far the back has been displaced. From this data, it is possible to calculate the stiffness of the spine. The equipment currently used to acquire this data is expensive, has a large footprint, and sometimes requires multiple operators. Due to this, there is a need to create a device which will increase accessibility of spinal stiffness measurements while also decreasing the size and cost of the device. We were successfully able to produce a functional prototype that meets these requirements. We will now give you a running demo of the SSI in action.
Now we're going to move on to the demo portion of our presentation. This here is the indenter control panel. Typically this shows on the Raspberry Pi touchscreen, but for ease of recording this presentation, I have it showing on my laptop. These options down here let us control the parameters for a stiffness measurement. First is a preload. This is a small load that initially gets applied to the back for a given period of time. Once this period of time elapses, we go and apply our main load. And this load also gets held for a period of time. When we apply our load, we can set how fast it gets applied using our step rate option. This controls the step rate of the stepper motor. Before we start a measurement, we first want to home the indenter. That's what our move up and down buttons are for. So let's start by moving the indenter head up into the fully up position. Now that that's done, we can begin our measurement. To do this, we hit our start button. As we see, data starts being collected from the load cell and we start measuring the displacement of the stepper motor. After a brief period of the preload time, we start moving up to apply our maximum load. Our maximum load is then held for our given period of time and the indenter head is retracted. All while this is happening, we continue to record our data.
Now that we have taken the measurement, it's time to save our data. To do that, we just press the save button and it opens up a save file window as well as an on-screen keyboard that can be used when you are on the Raspberry Pi. To save our data, we just name the file and press the save button. This saves our data onto the memory card. This graph can now be cleared using the clear button, and the previously taken measurement can be loaded using the load button. Another feature of this graph is that it's very interactive. I can move it around to look at different data points, and also zoom in and zoom out. And once we are done taking the measurement, we can press the exit button to exit out of the indenter control panel window and go back to the Raspberry Pi desktop.
Now let's talk about what is arguably the most important feature of the spinal stiffness indenter, the emergency stop button. This button allows us to quickly cancel a measurement and retract the indenter head. If we had a case for the device, one of these buttons would be embedded into that case, and the patient would also be given one of these buttons. Let's see how it works. So let's begin a measurement. The indenter head moves down, and once the load is applied, let's say that the patient starts experiencing some discomfort. All they have to do is press their button, and the indenter head immediately begins retracting. At this point, the graph also stops updating as we've cancelled our measurement.
Now let's talk about what we were able to get working. In summary, all our basic requirements and user stories were satisfied. We are able to manually move the indenter head in either direction into a known starting position. We are able to interact with the device through a clean, easy-to-use touch interface. We are able to collect data at a sufficient rate to make the measurements accurately. We are able to save, delete, and review the collected data and plot graphs in real time to visualize it as it is collected. We are also able to improve portability by minimizing the number of external connections to the device to just 3. Now let's talk about what we weren't able to do. Firstly, we are not able to get a good sampling rate using the HX711. When initially beginning the prototype, the HX711 chip was used as it implements both the ADC and the load cell amplifier in one inexpensive chip. However, it quickly became evident that this chip was not suitable for our application, as it would either overshoot or undershoot the required load value by many newtons. So we chose a discrete ADC and a load cell amplifier instead. Next, we were unable to compare the collected data against previous measurements, and by that I mean overlaying the graphs over each other to compare the current and previous results. Finally, we had planned to build an enclosure for the device, but after further discussion with the client, we decided not to.
In regards to future work or additions that can be made to expand the SSI in its current capacity, there are definitely features that can be added that will increase both the accessibility and extensibility of the SSI. The first possible feature is a combined measurements feature. This will allow the user to group all of the spinal stiffness measurements from a given patient into one plot that presents all of their session measurements. This gives clinicians the ability to analyze all data taken from a given patient, which would increase their efficiency in analysis. Another possible extension would be a telemedicine version of the application. This would allow the SSI to be run in a web or mobile application form versus the current desktop app. Clinicians can thereby operate and analyze data from a distance without having to be physically next to the SSI. Another reasonable feature that can be added would be including another axis of motion for the SSI. Currently, the only axis of motion is the z-axis, which moves the indenter head vertically up and down. Having only one axis requires users to shift the whole system physically in order to align the indenter right above the area which the load will be applied to. Incorporating manipulation of another axis would reduce the setup overhead of a system before a given measurement is taken. Another possible feature would be incorporating a database to store patient records. Currently, all patient records are saved in CSV format to the SD card of the Raspberry Pi. It would be better long-term to store the data in a database that would manage both patient info and corresponding spinal stiffness measurement data taken on a given day. Finally, the last addition that could be made in the future would be enclosing all of the electronics of the system into an enclosure. Currently, the Raspberry Pi has all associated circuitry in a proto board that is sitting on the Pi as a header or shield, but the rest of the subcomponents such as the custom load cell amplifier are not in an enclosure. This is because the current version of the system will likely not be the final version, and the capabilities of the system will be extended, so an enclosure in the interim would not be effective for long. This covers some of the features that would extend the current iteration of the Spinal Stiffness Indenter.
Well, we have come to the end of our presentation. To conclude, over the last 3 months, we were able to successfully create the next revision in the design process of the Spinal Stiffness Indenter with the guidance and support of our client, Dr. Greg Kawchuk from the Faculty of Rehabilitation Medicine. Thank you so much for your interest and attention. I hope this gave you a good look into our project. If there are any questions, we'd be happy to answer them now.